We're going to now find derivatives of logarithms of any base. So we previously found derivatives of natural logarithms. Now we're going to move on to when we have logarithms given bases other than e. When we work with logarithms, it's always helpful to go back and review what some of these values are so that we're keeping in mind what a logarithm really is. So log base 2 of 8, that's really just a number. It's just another way of saying 3. So just like 2 plus 2 is another way of saying 4, log base 2 of 8 is another way of saying 3. And we know that because 2 raised to, let me write this down, we've got log base 2 of 8. 2 raised to the third power is equal to 8. 2 cubed equals 8. Therefore, log base 2 of 8 is equal to 3. What's log of 100? Well, when I don't write a base, that's the same thing as base 10. So log base 10 of 100 would equal 2, because 10 squared equals 100. And if I have the log of 1/10, what would that be? Well, 10 raised to what power is 1 over 10? That would be -1. Now when you have base 10, so when you have a base 10, that's called the common logarithm. Base e is the natural logarithm. Base 10 is called the common logarithm. You may or may not recall that from a previous course. It's not always, teachers don't always call it the common logarithm, but it is, it's the common logarithm. Log base 3 of 81 is equal to what number? Log base 3 of 81 is equal to, indeed, it is 4. So it's a little quick review of evaluating a logarithmic expression without the use of a calculator. Another useful thing to know is the change of base formula. And we use the change of base formula to find exact and approximate values. So the change of base formula says that if you have log base a of x, that is equal to the natural log of the argument divided by the natural log of the base, or the common log of the argument divided by the common log of the base. And the common log is log base 10. So you can say log base 10 of x over log base 10 of a. In fact, it can be any base. It doesn't have to change, you don't have to change it to a natural log. You don't have to change it to log base e or log base 10. You could say log base a of x is log base b of x over log base b of a. The idea is that, let's use a highlighter so that you can see this. In every case, you're going to have the logarithm's argument in the numerator and the base in the denominator. So see how that base is in the denominator every time, no matter what base you change it to, you'll have the original argument as the argument in the numerator and the original base as the argument in the denominator. And you know that we have log base argument equals the exponent. Okay, so let's use the change of base formula to evaluate. We are going to need a calculator for this, and we're going to go out 3 decimal places. So log base 2 of 3. I personally like to use the natural log. I don't know why. I think a lot of teachers will use natural log because it's so useful when we're talking about compounded interest and the PERT formula and growth and decay formulas, but that's what I'm going to use. So I'm going to change these to natural log, or you could use log base 10. Either one of those buttons is on your calculator. In fact, you could also enter log base 2 of 3, but we want to use the change of base formula. So this would be the same thing as natural log of 3 divided by natural log of 2. Now it's not the natural log of 3 halves, it's the natural log of 3, which is some number, divided by the natural log of 2. And that value is, I need to next time write a little bit smaller. Approximately, what did you get? I got 1.585. So check to make sure that you can get that in your calculator. Okay, log base 3 of 60, that's going to be the same thing as the natural log of 60, which is just some number, over the natural log of 3, which is another number, and that is approximately what is that approximately? I wrote the problem down wrong, so I don't have the answer right off the top of my head. So let's see. I got this. I got about 3.727. So hopefully that's what you got as well. And then we've got log base 2 of -1. Oh, log base 2 of -1. This is most awesome. 2 raised to what power will give me a negative? Think about it, think about it, think about it. Yeah, there is no value. Remember, the argument has to be greater than 0. Therefore, this is not defined. We don't say no solution because we're not asked to solve anything. We're asked to evaluate it. What's that value? It doesn't have a value. It's not defined. There's no definition for it. Not defined. Okay, log base 2 of 5. I know that that's about 2 something. And I hope that you went right there too and said, oh, 2 squared is 4. 2 cubed is 8. So my answer should be 2 raised to the between 2 and 3 power, right? So somewhere between 2 and 3, somewhere between 2 and 3 is going to be our answer. So log base 2 of 5 is going to be the natural log of 5 divided by the natural log of 2, which is approximately 2.322. So hopefully you got those values. You're feeling pretty good about the calculator. Now we're ready to move on to some calculus. Now this goes pretty quickly, so don't blink. The derivative of a to the x, and I would make flashcards. This is really where I would make flashcards and know my derivative laws. So on the first side I would put what's already written down there in blue, d dx of a to the x. And in the back I would put the natural log of a times a to the x. So the derivative of x, or the derivative with respect to x, so sorry, the derivative of a to the x with respect to x is the natural log of the base a times a to the x. Now, if x is more involved, this is when x is 1x. When you have 1x in the exponent. When you have another more complicated exponent, you're going to have the natural log of a times a to the u times the derivative of the exponent, du dx. So it's starting to get a little bit more complex, and that's why flashcards will help. The derivative of log base a of x with respect to x is 1 over the natural log of the base times 1 over the argument times, that's it, because it's just an argument of x. So when the argument equals 1x. But when the argument is more complicated, you're still going to have 1 over the natural log of the base times 1 over the argument times the derivative of the argument. And you can think of this first one as times the derivative of the argument times 1. We just don't write that because we don't have to multiply by 1. Okay, so let's practice. Let's find the derivative. G of x equals log base 5 of 3x. Well, g prime of x is going to equal, let's see if you can use the formula. Okay, if you're back, you should have 1 over the natural log of the base times 1 over the argument times the derivative of the argument. The 3's cancel out, and we're going to have g prime of x is equal to 1 over x times the natural log of 5. Okay, this next one, number 2, you should be able to try number 2. Number 2 is going to involve the product rule because you have x times 3 raised to the x plus 1. So you have 2 factors here. So we're going to have the derivative of, you can try this one. If not, you can work along with me. Derivative of the numerator, not the numerator, the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. And the derivative of the second factor is the natural log of the base times 3 to the x plus 1 times the derivative of the exponent. So the derivative of the base times the exponential expression itself times the derivative of the exponent. And that's equal 3 to the x plus 1 plus x natural log of 3 times 3 to the x plus 1. So both terms share a 3 to the x plus 1, so we'll factor that out, and that's going to leave us 1 plus x natural log of 3. Okay, here's a couple for you to try. Here, try finding the derivative of y equals 1/4 raised to the x power, and try y equals 10 raised to the x squared. Okay, I didn't press pause, so if you pressed pause, you're probably going, well, I gotta wait now. Okay, you don't have to wait too long because I'm going to go right to the answer here. dy dx is equal to the natural log of the base, which is 1/4, times 1/4 to the x times the derivative of the exponent, which is 1. So that's really the answer right there. You could rewrite it, I guess, 1/4 raised to the x power times the natural log of 1/4. You could also write it like this. 1/4 to the x times the natural log of 1 minus the natural log of 4. The natural log of 1 is 0. So you would have, yeah. No, I mean, that was fun to do that, but I like that answer the best. So we're just going to leave it right there. Okay. Next one, y equals 10 raised to the x squared. You're going to have the derivative is equal to the natural log of the base, 10, times the actual base raised to the exponent itself, times the derivative of the exponent, which is 2x. And again, there's not much you could do there. You could rewrite it. They might write 2x first, and then maybe the natural log of 10, and then maybe 10 raised to the x squared power. Who knows how they'd write it, but that's the answer. Okay, in the next video, we're going to come back and we're going to do these word problems. And maybe a little bit of implicit. Yeah, I think I'm going to throw in some implicit and maybe a second derivative in there. So we're going to do this word problem and just a little bit of implicit differentiation, because that's always a good thing to remain skilled at.